Buenos días a todos nuevamente. Lamentablemente nuestro primer y segundo expositor, Kyriakos Validakis, no se ha podido conectar a la plataforma. En estos momentos y para respetar el cronograma y el horario de los demás presentadores, vamos a mantenernos a la espera. A la hora 10 comenzaremos con Rosa Paccione, que nos dará el tema estimaciones de ZTD en redes regionales e internacionales y contribuciones a la climatología y la meteorología. Vamos a seguir a la espera a ver si Kyriakos puede conectarse. Él está en Alemania en estos momentos y si puede conectarse antes de las 10, comenzaremos con su presentación. Si no, esperaremos para mantener el cronograma. Les pido disculpas nuevamente por estos inconvenientes y que permanezcan conectados, que ya volveremos. En estos momentos pudo conectarse Kyriakos. Kyriakos, welcome to the virtual school. I don't know if you can hear me.
Hello.
You can hear me?
I can hear you. Can you listen to me all right?
Okay.
Super.
I want to introduce Kyriakos Validakis. He want to talk about remote monitoring of the atmosphere. So, Kyriakos, the school is yours. If you
can I? How can I share my slides?
You can share from the app.
It says host disable. Okay. I cannot share.
Oh, you're a panelist?
I'm not sure.
Yeah, you are.
Okay, so there is this button, share screen.
Yeah.
And I cannot, when I press it, it says disabled share, host disabled attendee screen sharing. And so what can I do?
Let me change your role again. Now, can you share it now?
I'm sorry, it's the same thing.
Same things. Let me. Let me check again. Let me put it like a co-host. Now, try again.
Okay, something is happening.
Or if you have a presentation, you can send me and I can share it.
Okay, 1 second. Please give me 1 second. Okay, does it work now?
Perfect.
All right. So so I prepared a very long, a rather long set of slides for this school. The first part has to do more about yeah, describing and understanding the atmospheric delays with which we have to deal with in space geodesy, and then the second part are some thoughts about the atmospheric ties. So in space geodesy, in geometric space geodesy, we're mainly concerned with four space geodetic systems. So in this picture, you can see the global navigation satellite system. On the left, you have the ground station network from one of the IGES Repro 3, and on the left you have the tracks of the orbits of about 120 satellites for one day. Then we have the very long baseline interferometry technique. So with VLBI, we observe we have fewer stations, less than 50 active stations around the world right now, and we observe extragalactic radio sources, quasars. Then we have satellite laser imaging. Unlike GNSS and VLBI, this is an optical technique that operates mainly at 532 nanometers. There are about 35 stations. Here plot the tracks of about 9 spherical satellites. And last but not least, we have the Doris system. It's a French. There's an excellent ground network, again, around 50, 60 stations. And yeah, and here you see the tracks of the satellites that are tracked by the Doris system. So why are we in space geodesy? We're mainly interested in the estimation of position. Why is troposphere important? So we estimate northeast up component for the station position. We estimate clock. We estimate also we have this zenith delay and gradients, and this is if you analyze GNSS data for let's say an hour and you obtain the covariance matrix. And from this covariance matrix you obtain the correlation matrix. It looks like that. So what we see here is that there are some very important correlations between the non-hydrostatic delay, the zenith atmospheric delay, and then the clock and the height, the radial displacement. And also there are some significant correlations between the gradient north, gradient east, and the east and north station displacement component. So this is, I think, some motivation that tells us why there is this interplay between troposphere clocks and positioning in the space geodesy. So these are four techniques. We have three techniques operating in the microwave spectrum: GNSS, VLBI, and Doris. So lowest is Doris. Doris has 2 bands, 0.42. GNSS has 1.2, 1.5 gigahertz, and VLBI starts from 2 and goes up to 14 gigahertz for space geodesy. So SLR operates usually in the 532 nanometers, but there are some also infrared systems. So the signal propagation. What we want to know in space geodesy is the difference between this red line and the black line. The black line is here symbolized as the time it would take the signal to come from the satellite to the station if there was no atmosphere. So, but what happens in reality is that the signal that is emitted from the satellite is bent, travels along a bent path, and travels at a speed that is slightly smaller than the speed of light because of refraction. Now, this delay depends on the direction, the frequency, and of course the density of the medium. It matters the electron density that we have in the ionosphere, and also the pressure, temperature, humidity in the troposphere. If you write the equation, you can express it in terms of propagation delay and in terms of ray bending. So how much more time it takes to travel along the bent path, and what is the difference between traveling in a straight line as opposed to a bent path. So the ray bending is only important if you go to very low elevation angles. So at higher elevation angles, it's higher than 30 degrees or something. Ray bending has almost a very small contribution, almost zero. So to do all that, we need to know the refractivity. And for the ionosphere, it is a function of the electron density and the magnetic field. And for the atmospheric component, it is a function of the pressure, water vapor pressure, so humidity, and temperature. So we said before that we have three techniques that operate in the microwave domain: GNSS, VLBI, and DORIS. And so these techniques, to calculate their refractivity, for these techniques, we need pressure, temperature, humidity. And for the optical refractivity, so SLR and also lunar laser ranging, in addition to pressure, temperature, humidity, we also need the frequency of the signal. So the delay is frequency dependent. And also in these equations for SLR, there is a small term that says that the hydrostatic delay for optical signals depends also on the concentration of carbon dioxide. However, this is a very small component. Now, we can decompose this, the refractivity, we can decompose it into two parts. The first is the hydrostatic part. And the hydrostatic part is something that is very predictable, right? And then we have the non-hydrostatic component, and the non-hydrostatic component is mainly due to the water vapor in the atmosphere. And this is not very predictable. And this we usually have to estimate employing the space theoretic measurements. Now, let's discuss for a second about the ionospheric effects. So for microwaves, the ionosphere is a dispersive medium, which means that if you have observations at two or more frequencies, you can mitigate first-order ionospheric effects, and this is known for many years, and this is done. And this is why in GNSS and VLBI and DORIS, we always observe at least two frequencies. There are many ways to do it. One of the ways is to apply something like that. And if you do the error propagation in this equation, you will see that you sacrifice reducing or almost eliminating a systematic effect for noise. So these P3 and L3 observations, they will have a higher uncertainty compared to the single frequency observations. For VLBI, something similar happens, and so for GNSS, VLBI, and DORIS, there are also the so-called higher order terms, but they are again a function of frequency, and the higher the frequency, the smaller these terms. So for VLBI, for example, these higher order terms are, I think they're not applied because the contribution is extremely tiny. So the movie I created here is based on global ionospheric maps from processing with GFGX, and it shows how the vertical total electron density changes throughout the day. And you see that it closely follows the movement of the sun. And if you take a time series either from VLBI, as you can see in the top panel, or GNSS in the lower panel, this vertical total electron content, it has some annual variability, and it also has this. Now, to understand and better do better job in terms of atmospheric delay calculations for space geodesy. One of the tools that we use is ray tracing. So ray tracing is extremely important, and the way it works is that if you know where your station is and where the satellite is, you also um, find out the atmospheric density in between, and then what you do with ray tracing is that you find the path that the signal will follow to come from the satellite to the station. So after you find this path, then you do a simple numerical integration, and you have calculated the delay. The state of the art, the accuracy of this ray traced delays, atmospheric delays that we can calculate based on state of the art models, they have an accuracy about 1 centimeter in the zenith, and if you look at lower elevation angles, then it gets the uncertainty grows. Now, the problem with this ray tracing is that while it's very accurate, it's also extremely expensive. So if you want to use a meso beta scale model, so like R5, which has a temporal resolution of 1 hour, and if you use the model level data, you have something like 137 levels, 30 kilometers. It costs about 18 terabytes per year to just from a disk storage viewpoint. Also, this is a very intense procedure to do the ray tracing, and this is why we use a parameterized version. And you can parameterize the delay as a function of direction, and then there are some empirical models for time, for example, that you don't need to calculate the delay every hour, but you have annual, semi-annual, diurnal, semi-diurnal harmonics to describe the delay. The most common parameterization is the following. So on the left, you have the atmospheric delay as a function of elevation and azimuth at a certain epoch, and it is decomposed into the symmetric, the so-called symmetric delay. You have with this MF, this is the mapping factor, and here you have a zenith delay. So the first part with the subscript H is the hydrostatic. This is delay because of dry gases, and this is something very predictable, right? We can know with very good accuracy in advance. Then the second part, the second addend, the NH is non-hydrostatic, and this is mainly due to water vapor. And our numerical weather models cannot describe this very accurately. In addition to the symmetric delay, we have the asymmetric delay. You see in the first line, everything is a function of elevation angle, epsilon. And in the second line, we see that we have the azimuth that appears in the equation as well. And the symmetric delay, we have these so-called gradients, okay? And so we said that the gradients and the non-hydrostatic delay, which is mainly due to water vapor, they are not very accurately predicted by weather models, and this is why we estimate them based on the space geodetic observations themselves. So the parameterization is extremely important. So please try to follow me in this graph. This is a snapshot of the atmospheric delay at one random station at one epoch. The horizontal axis is the azimuth from 1 to 360 degrees, from 0 to 360 degrees, and then the vertical axis is the slant delay at an elevation, at a very low elevation angle. So if you choose to use only the symmetric delay, then your model is a straight line. However, you can see that this bold, this strong line, it shows that the delay is not constant as a function of azimuth, but changes very much. And if you look to the units on the right hand side, you can see that the variation reaches almost 1 meter. And given that our observations in GNSS and VLBI, they have an uncertainty in the order of millimeters, then this is an error that we cannot afford to have in our analysis. And this is why we should really take into account the gradients in modeling the atmospheric delay. So if Later on, we will talk about differences between GNSS and SLR, and it starts from again from the modeling viewpoint. We have the north-south gradient for microwaves. It looks like that, and then for optical, so for lasers for SLR, at a certain epoch, it looks like that. So what we can see is that on the southern hemisphere, the north-south gradient is mostly positive, and in the northern hemisphere, it's mostly negative. And this is why because of the flatness of the Earth. That's why. And that the fact that the atmosphere, the depth of the troposphere is bigger at at the equator compared to the depth of the atmosphere at the poles. Then we also have the east-west component, which is it is less systematic. We said before that these atmospheric delays, they can be quite uncertain. The graph here illustrates the zenith-wet delay from era 5, so one epoch minus the long-term average. So you see that the signal can change, can change, let's say plus minus more than 20 centimeters. And then we have also some other components of the delay. So, but they are not. We have the hydrometeors, and then we have the gradient amplitude. So if you take two state-of-the-art models, that's what I did here. I took R5 and also ICON. ICON is a model. It has a spatial resolution of 13 kilometers global, very accurate, state-of-the-art. And if you compare R5 with ICON, we see here that the differences in terms of the zenith delay are larger than several centimeters. So we cannot simply take the zenith wet delay from a weather model and use it in our analysis, because simply which model to use. So they are not accurate enough in this regard. We need to estimate the atmospheric delays and gradients, the zenith delays and the gradients. We need to estimate them based on the spatial data. Now, I took here 2 weeks of data, and here I plot the so-called zenith total delay. In the black line, you see at the station in Germany, what is the zenith delay for GNSS station, and then for exactly the same location, what is the zenith delay if we have an SLR station. So we notice two things from here. The first is that for SLR, so the optical delay, it is much smoother. That's first, because the laser is not as sensitive to water vapor as microwaves. First, more smooth, and then second, at this frequency, 532 nanometers, the green laser, the zenith delay is slightly larger. That's the first. Second, for the gradients, we see that the GNSS gradients, they are, let's say, quite noisy time series, but the gradients from SLR, they are also very smooth. And this is again due to the absence of water vapor. This is here the west coast of Australia, and here there is a magenta dot for a station called Yarragadee. So what I did here is I did ray tracing for a long period of time, and then I calculated the gradient amplitude here at this station, and then I calculated the gradient amplitude at all the pixels that you see within this picture. After I did this, I took the time series at Yarragadee and the time series for the other pixels and calculated the correlation coefficient. So you can see that the closer somebody is at Yarragadee, the higher the correlation, right? And this is for microwave gradients. Now, if we change the frequency and we switch to the laser, we see that for optical frequencies, so for the lasers, the signal is spatially more coherent. So for microwave, it decorrelates very fast. For optical, it does not change very much as a function of distance. Now, we will talk about atmospheric ties in some minutes. So we have the atmospheric delay can be parameterized as a function of height. So if what happens if we go what happens to the atmospheric delay if we go 100 meters higher? So for the hydrostatic component, this is what we can predict very well. More or less, if we go 100 meters higher, the delay will decrease by almost 3 centimeters. Why is that? Because the signal travels to an atmosphere that is less deep, 100 meters less deep. Then for the non-hydrostatic component, again, if we go 100 meters up, then the non-hydrostatic delay will also be smaller by 3 millimeters. And so I also did this exercise for the gradients. We see that the gradients, they also are smaller. However, they are not, let's say, significantly smaller. Now, so the space-side geodetic techniques that we use in geodesy, they observe at different frequencies. And when we calculate the atmospheric delays, the ionosphere is usually not considered. However, although ionosphere does not affect the tropospheric delay directly, it affects the ray path. So by changing the ray path, it indirectly affects the tropospheric delay because we need to integrate at a different path. So VLBI, as we said, has two frequencies. This is the legacy system, 2 and 2.3 and 84.4 gigahertz. This is the highest frequency, 8.4 gigahertz. You see that if you take into account the atmosphere in the modeling or not, then the differences are very small. So 0.01 millimeters, this is very tiny. However, when we go to 2 gigahertz, we see that the difference is again sub-millimeter level. So for GNSS, it can exceed the millimeter level in some cases. And the third microwave system for geometric space geodesy, DORIS, we see that the difference can be quite large. So DORIS, the lowest frequency for DORIS is 0.4 gigahertz. And we see that if you don't take into account the ionosphere during modeling, you can have an error at the several centimeters level. Another issue when modeling the atmospheric delay using numerical weather model data is the orbital altitude. So the closer a station, the smaller the distance between the station and the satellite, the larger the bending. So for VLBI, the distance is infinity, billions of light years away, and for GNSS, so the difference between GNSS and VLBI is very small. So at an elevation angle of 7 degrees, it is sub-millimeter level, right? But when we compare the delay between DORIS and VLBI, we see that the difference can be quite large. And this is why the satellites that are used during DORIS data analysis, they have an orbital altitude between 7 and it's always below 2,000 kilometers. So the lower the altitude, the higher the higher the slant delay. Another example that I put here, so if we want to track the GRACE follow-on satellite mission using satellite laser ranging, there are, currently two mismodeling shortcomings. One is that the orbital altitude is not taken into account. So this will cause the atmospheric model that is used for SLR to be biased by almost 1 millimeter. So all the range is biased by 1 millimeter. And then the second is that although laser observations are affected by gradients. There is no modeling, so they're usually not modeled a priori, and they are also not solved during the processing. And yeah, this causes that the slant delays, they can be wrong by several centimeters if your station is, let's say, is not in the equator, and SLR has no stations within the equatorial belt. Now, a few words about yeah, now we know what can be estimated with space geodesy. We know also some details about differences between microwave and optical delays. So how can all that be used? So there is this technique called radio occultation. So, and this is this red line here. And with this, you can derive profiles for example, humidity, temperature, and this is very important information that ends up into numerical weather models, and is since decades is a very important observation. Then something else that you can do is you analyzing GNSS data, you have to estimate the zenith delays and the gradients. Why? Because the weather models are not accurate enough, so we cannot fix them to some a priori values. And then we can use these zenith delay and gradient estimates to improve the numerical weather models by a process called data simulation. Another thing that we can do is we can take we can compose a very long time series. So from this zenith delays, we can eventually calculate the integrated water vapor and calculate integrated water vapor trends. Now these are very important because water vapor correlates with temperature. So an increase into water vapor is associated with an increase in temperature. So if we want to be able to better probe global warming, this is a very good tool. And last but not least is reflectometry. And with reflectometry, we can deduce the ocean surface, the roughness, and from this we can calculate the wind speed, and we can also so for stations that are, let's say, on soil or on land, we can calculate soil moisture in the immediate vicinity of the station. So a colleague from GFZ published an article recently, and this article is about the simulation of GNSS delay. So if you put just one observation, one zenith delay observation and one gradient observation in the numerical weather model, you see the impact it has. So this is a map of Germany. So just for an observation, you see how much impact it has, the zenith delay on the right and the gradient on the left. And then here in these graphs, you see on the vertical axis you have the height, and then on the horizontal axis you have the latitude, and you can see the extent to which assimilating either one ZTD or one gradient measurement with a very generous uncertainty affects the water vapor mixing ratio field. So nothing will happen after 6 or 7 kilometers if you put just one observation. Yeah, so so far we discussed about we said why studying the atmospheric delay is very relevant for space geodesy, because there is the correlation between the delay, the position, and the clock. Numerical weather models, we established that they are indispensable for the reduction of the space geodetic data, but they are not accurate enough, and that's why we need to estimate zenith delays and gradients in while we're processing GNSS VLBI and DORS data. We said that the optical delays, they are different than the microwave delays. They are smoother both in space and in time, and that the atmospheric delay coefficients, they decrease with altitude because the depth of the atmosphere is the signal simply has to travel less troposphere. Yeah, the GNSS derived atmospheric delays, what we do during the geodetic processing can be used, this byproduct can be used to improve weather forecast, and it is done by some weather services. Yeah, we have together with my colleague Florian and some other colleagues from GFZ, we published recently a software that you can download from GitLab, and you can have You can there are examples, there are data associated with it, and you can do your own ray tracing and calculate figures like the one that I have presented by yourself. It's very easy. There is a README file, and yeah, so feel free to use it. And now a few words about atmospheric ties. Um, I'm going to start with VLBI. So in VLBI, very long baseline interferometry, we said that we have some station on Earth, we observe extragalactic radio sources, and we want to estimate parameters. What do we estimate? So our normal equation will be populated by a block that has station coordinates, another block that has the right ascension and declination, so the coordinates of these extragalactic radio sources. Then we have Earth orientation parameters, so polar motion, UT1 minus UTC, length of day, precession notation, celestial pole offsets. Then we have this tropospheric delays, what we discussed before, so zenith delays and gradients. We have clock parameters, so VLBI stations are equipped with active hydrogen masers. They have a precision of about 10 in the minus 15. And we need during the processing to estimate some functions to describe the behavior of these frequency standards. And then there are some other systematic effects that we also need to take into account when we are analyzing VLBI data. So our normal equation matrix has these blocks, and some of these parameters, they are interesting for other techniques and can be derived by other techniques, such as the station coordinates, the Earth orientation parameters, and the tropospheric delays. So if the parameters are not identical, then we need to have these so-called tie vectors. So we have, first of all, the local ties. So when we're going to combine station coordinates, when we combine Earth orientation parameters, we have the global ties. Here, the vector is implicitly 0 because the same Earth rotation parameters that we estimate using VLBI data are the same Earth orientation parameters we expect to estimate using SLR or GNSS or DORIS. And so we can do the same thing with troposphere, of course, taking into account the things like the height difference between the stations. We can combine clocks. So there are quite a few stations where the GNSS station is connected to the hydrogen maser of the VLBI station. So in principle, the clock you estimate in VLBI and the clock you estimate in GNSS during PPP should give you the same result. So for the state of the art says that the combination, the inter-technique combination should be done using local ties and global ties, and there are some experimental combinations using tropospheric ties, clock ties, and also satellite ties. So if you observe satellites, which we currently do not do with VLBI, but will do with the Genesis mission, which will be launched by ESA in a couple of years. What are these ties now? The definition, let's say, how I understand ties are that they are the expected differences in the parameters that we mentioned. They need to be external, and they need to be more accurate than what we can get from the spatial-theoretic techniques. Why do we need them? Because they facilitate the combination of the techniques, and that way we can exploit the strength and mitigate the weaknesses from the different techniques. Then we can do datum transfer. For example, VLBI does not observe satellites, so it does not know where the center of mass of the Earth is. But when we combine VLBI with SLR, SLR observes low Earth orbit, observes satellites that orbit around the center of mass of the Earth. So when we combine VLBI with SLR, this information is transferred from SLR to VLBI. And then, since we can estimate the same things using different independent observing systems, we can detect technique-specific issues. On the right here, you can see some sky plots I created quite some time ago, and they illustrate how the targets appear from the GNSS viewpoint, VLBI, SLR, and DORIS. And you see that for example, in techniques like Doris and VLBI, the observation is relatively poorer compared to GNSS. So if you want to have a good tropospheric delay estimation, VLBI and Doris will benefit from a combination with GNSS. So we said that we need this external information. We get this from a local service for the local ties. For the atmospheric ties, we get this information from usually from numerical weather models. For clock ties, there are systems in place in currently very few stations that the cable delays can be measured exactly. And for satellite ties, well, it's like a local survey, but you have to do it before the satellite is launched into orbit, because after that, there's not much you can do. Now, there are some discrepancies between what this external measurement gives us and what we can measure with the spatial-theoretic techniques. And so this is in many cases due to inconsistency in modeling and parameterization. There are some undetected systematic errors in the individual techniques, or there is some error during the measurement of the local ties. So in many of these systems, there is no single point that you can track and say this is at the center of the VLBR or the SLR system. It's many times it's an intersection of axes, which is no material point. For example, here, in the graph here, you see on the horizontal axis the time, on the vertical axis you see the zenith delay differences between two stations. So I have already applied the expected atmospheric delay using R5 data. So if there was an agreement between the generic measurements and the weather model, there should be just some noise around zero. But this is not the case. What you see here is that there are biases, and these biases, they vary as a function of time. So this pair is something that should be revisited. What do we do when we detect such tie discrepancies? We can choose. If we have time in our hands, we can improve the modeling, parameterization, and the consistency of the techniques. We can do some more measurements. This is for example, for the local ties, and if we don't want to do some improvements or do some measurements again, then we can simply downweight the local ties that do not agree with the results. We have already discussed this. So this is the covariance matrix. There are high correlations between displacement, zenith delay, and clock. That's why we are so much concerned with the modeling of the atmosphere. And these so-called atmospheric ties have been successfully applied in GNSS and the VLBI combination for many years. There are many papers about that. Many people have done it. And so we have a project where we do combination, not at the normal equation level, but at the observation equation level. So we have software that is able to do VLBI GNSS SLR combination. And so this is an example. On the vertical axis, you see the weighted root mean square error of position time series during a 2-week period. And what you can see here is that, for example, in green, you have the WRMS of the VLBI only solution. And then in blue, you have the solution, the combined solution, GNSS VLBI, where local ties, global ties, and atmospheric ties are combined. So local ties, position, global tie, Earth orientation parameters, polar motion, length of day, etc. Atmospheric ties, zenith delays, and gradients. And you see here that the RMS improves by more than 10% in the north and east component, and close to 40% in the up component. Now, atmospheric ties in practice. What are these atmospheric ties? They are, in essence, stochastic equivalence constraints. So the parameters we're concerned are the zenith delays and the gradients. And so, for example, what we constrain is the difference. We say that the difference between, for example, VLB and GNSS and ethylate cell should be the same as the expected difference from ERA5 plus minus an uncertainty. So when we apply atmospheric ties, we need to make some decisions. So first of all, where do we get our atmospheric ties? Do we take them from a numerical weather model? Which one? Then second is, do we apply bias correction? So some GNSS stations are equipped with a protective dome, a radome, and this has some, it causes a bias in the delays. So do we empirically remove this? Do we leave it in? What do we do? Then the atmospheric delay changes within a couple of minutes, but the difference between the atmospheric delays of stations that are nearby does not change as rapidly as a function of time. So do we apply something? Do we apply a constraint every hour, or do we just have a time invariant constant? Also, what uncertainty do we apply to this pseudo-stochastic observation? Yeah, before I continue, I would like to ask the organizers, how are we doing on time?
In fact, we are 6 minutes late, so I don't know
Okay.
how much time do you need.
Yeah, I think I will. I would like to take questions now.
Okay.
Because later on it gets more detailed, and so I think that all the important information about atmospheric delay modeling and what is going on with the combination and the ties has already been described. So I'm happy to get questions if there's time. If not,
Kriakos,
yeah.
if you need, maybe 10 minutes more.
I'd rather have questions, because then it's what I have later on is an example from a study, and it's quite detailed.
Continue with your presentation. Don't worry.
All right. Okay. Thank you. Okay. So we did a couple of years ago. We did a study, and in this study, we wanted to combine GNSS, VLBI, and SLR data. So we have the networks are very different. So for GNSS, we have almost 250 stations globally distributed. For VLBI, we had only less than 20, and for SLR, we had less than 30 points on the planet. This is for a 2-week period. So the way to do it usually is you say that the Earth orientation parameters between these three techniques, they are equal, and then you also combine with the so-called local ties. So local ties, it means that next to a VLBI station, in a distance of 50, 100, 200 meters, there is an SLR station or a GNSS station, and the difference between the distance is very accurately measured by a surveyor. So we see that, for example, for GNSS, from the 244 stations, we have local ties for less than 10% of the network, right? So very few. I think this graph here on the right might be quite interesting to understand a little bit what's going on when we combine data from different observing systems. So there are 3 columns: GNSS, VLBI, SLR. The orange is number of observations. The purple is the number of parameters that are estimated during the processing. And then the y-axis is just number, and the scale is logarithmic. What you can see here is that the difference from SLR to VLBI and from VLBI to GNSS is more than 1 order of magnitude. So this should somehow be taken into account, the combination, by appropriate weighting. So how the combination is done, we start from the VLBI group delays for VLBI, then we have GNSS and SLR. So for SLR, we analyze data for Lagios 1 and Lagios 2 only. Then we do the single technique analysis, and so for VLBI we have station coordinates, radius ascension, declination, earth orientation parameters, and atmospheric delays. So as we said before, and for GNSS we have station coordinates, earth rotation, zenith delays and gradients, and for SLR we have station coordinates, range biases. This is an SLR station and satellite specific instrumental effect. So it's a fudge parameter that has to be estimated. And yeah, also polar motion, length of day, and zenith delays. Then we have the single technique solution, and then we take these three solutions and we get the combined solution with local, global, and atmospheric ties. So for the local ties, in total there were 36 vectors, and so local ties is station coordinates, global ties is earth rotation parameters, atmospheric ties is zenith delays and gradients. And so in this study we chose to there were two approaches, and in one approach we constrain the difference between the delays at collocated stations. So we say the difference between, for example, GNSS and VLBI should, this is the measured difference, should equal the difference, the expected difference that we get from a weather model. And then, as we said before, we need to decide what uncertainty to put on this pseudo observation equation. And we had let's say 4 choices from 1 millimeter to 1 centimeter. And then we did an experiment to the scaling approach, instead of constraining the differences, to constrain the ratios. We did many solutions. We have a reference solution. This is the standard, what is done usually. So local and global ties, so positions, station positions, and earth orientation parameters. Then we have the scaling approach, and then we have the difference approach. There are lots of results here, but I would like to let's say skip some, if I may, and go directly to the summary and the conclusions. Time has passed. So when we combine GNSS, VLBI, and SLR, the normal equation, we can use atmospheric ties in addition to local and global ties. We see that the station coordinates and baseline length precision gets improved if we have tight atmospheric ties. So tight atmospheric ties was 1 millimeter. The local tie discrepancies improve if we have loose atmospheric ties. The rest of the results are, let's say, rather expected. So in principle, if you impose loose atmospheric ties, it means that the influence of the atmospheric ties on your solution is not very big. However, in our consideration here, we used uniform weighting for the ties, and this is probably not very correct. Why? Because we found some biases, and we did not eliminate them. So, for example, for the stations that had biases, we either should have corrected them or downweighted these observations, and this would benefit the combined solution. And if one wants to repeat this line of work, currently it is impossible, because there exists no SINEX file from VLBI, GNSS, and SLR that contains these three sets of parameters that we combine here, which is the station positions, Earth orientation parameters, and atmospheric delays. What you usually find in these SINEX files are Earth rotation parameters and station positions. You currently, to my knowledge, there are no SINEX files that contain atmospheric delays. And the important thing is not the atmospheric delays themselves, but the covariance matrix between the atmospheric delays and the station positions. This is very important. Yeah, I think that's all. That's more or less I have for now. We have a project on the topic of combination of space geodesic techniques with atmospheric and clock ties. And yeah, we're busy at work to do this at the observation equation level. And yeah, if you're interested in the topic, yeah, get in touch. Thank you.
Thank you very much for your presentation. It was a pleasure for our community to take you in our school. There is one question. There were two, but I answered one about the ERA 5 model. So the question is Bruno Kimusleisri. Please, some lights on the impact of a mapping function in the tropospheric computations?
Yeah, so yeah, let me go to slide. Yeah. Let me go to an appropriate slide. Yeah, so the mapping function that the colleague refers to is this guy here. This is for the hydrostatic component, and then this is for the wet or non-hydrostatic component. So this mapping function, the state of the art says that you do, so let's say that you have a station of interest. What you do is you do ray tracing at 10 different elevation angles, starting from 3 degrees up to 90 degrees. And you do this for many azimuths. So you start looking at the north, and then you turn, you go to, for example, 30 degrees, 60 degrees, 90 degrees, blah, blah, 270, 300 degrees. So you have now all these ray traced delays. And so when you look at the zenith, the delay should be about 2, if you're at sea level, 2.3 meters. And if you look to the horizon, it can be close to 30 meters. So this mapping function is a quick way to describe how the zenith delay increases as a function of elevation angle. Now, this delay, this function, this is the mapping function. It depends on mainly on the weather model data that you used. So if I calculate one with ERA 5 or with MERA 2 or another model, the mapping function will be different. There have been many papers since starting since 20 years ago, comparing the impact of different mapping functions. In principle, I think the case is that the more, if your model is more state of the art, if it has higher spatial and temporal resolution, then the more accurate is the mapping function that you're using. So that's one thing. So if you can, you should, in deriving the mapping function, use a as high resolution model as possible. One, and two is that there are two, let's say, schools of this mapping function. One is you get coefficients for every epoch. From a TU Vienna, for example, you have coefficients every 6 hours. This is one approach. And then the other approach is you don't download data every 6 hours. You simply download some coefficients, and you can approximate the time series of this mapping function as a function. So you have some seasonal signals, so annual, semi-annual, diurnal, semi-diurnal, and yeah, so so this approach with the empirical approach with the coefficients, it is of course cheaper. If you're a user and you want to apply, you don't need to download stuff every day, four times a day. You just download the coefficients and you have them there forever. But of course, this comes at a cost, and the cost is reduced accuracy in the atmospheric delays you derive, and also the station coordinate positions. So the worse, if you do, the better atmospheric delay modeling you do, the better station coordinates you have. So the station coordinates and the station coordinates and the atmospheric delays, they're in the same adjustment. So if there is lots of error in the atmospheric delays, it somehow propagates into the station positions as well. So yeah, I hope this is remotely helpful. Then there is also another question. Aside from the needs, so first of all, is this covered? Should we move to the next one? Okay. So aside from the need for SINX files containing atmospheric parameters, what do you think should be done, or what infrastructure is necessary to implement to improve or increase data to determine atmospheric ties? Well, for atmospheric ties, so yeah, I mean the main component in atmospheric ties is the height difference. So yeah, using simply the hydrostatic, assuming the atmosphere is in the hydrostatic equilibrium, and calculating the zenith delay difference based on that, in most cases you are not very wrong. Otherwise, best is of course if you download the weather model data, calculate the delays at exactly your locations, and then calculate the differences. This is of course the best. But if this is not possible because of technical difficulties, I think there are institutes. So Vienna provides grids of zenith delays, and you can do this from there. However, yeah, to my recollection, these grids are quite coarse. So I think there is a version of 1 degree and then another version of 2 times 2.5 degrees. So 1 degree is about 100 kilometers at mid latitudes. So, and then the collocations are maybe 50 meters away or 100 meters away. So yeah, I'm not sure how well this can be captured.
Thank you, Kyriakos. We haven't got more time, so
Okay.
we need to continue with the other presentation.
Okay.
If you could, please, in the break at 11:20, you could tell us more details about the software that you mentioned.
Okay. I'm here. Thanks for the questions.
Thank you very much, Kyriakos, for your presentation. Les recuerdo a los de habla hispana que este video será subido en breve con su traducción por subtítulos, que es un trabajo que está haciendo Virginia Mackern en forma artesanal, a la cual le agradezco mucho todo el esfuerzo que está haciendo para realizar las traducciones de los videos de toda esta escuela. En breve lo subiremos a las redes sociales y a la página web de CIRGAS con los subtítulos en español. Virginia, ¿querés presentar a la siguiente presentación?
Sí, bueno, la siguiente presentación es de la doctora Rosa Paccione. Ella nos hablará sobre la estimación del ZTD en redes regionales e internacionales. Zenith Total Delay Estimation in Regional and International Networks by Rosa Paccione.
Good morning, good afternoon, and good evening to the online participants from all over the world that are watching this video. I am honored to have been invited by CIRCAS to contribute to the virtual school in terrestrial reference frame, geodynamic and atmospheric monitoring, to talk about zenith total delay estimation in regional and international networks and its contribution to climatology and meteorology. This presentation is divided into 4 sections. In the first section, I will give an overview of the IAG international and regional ground-based networks. The second section will focus on the tropospheric estimation, how we get zenith total delay and integrated water vapor from the observation. In the third section, I will show example of tropospheric monitoring at ground-based networks with a focus on EPN activities. In the last section, requirements and application to climate and meteorology will be provided. The IAG services, the International GNSS service, the International VLBI service, the International DORIS service, and the International SLR service generate products by collecting and analyzing their own observation, relevant for geodesy and for other sciences and applications. Accuracy and robustness of the products, quality control, timeliness, and state-of-the-art quality are the essential aspects of the services. We will focus on the 3 microwave techniques: GNSS, VLBI, and DORIS, whose activities are organized and coordinated in the framework of the IAG services, IGS, IVS, and IDS. Each service has a ground-based tracking network that is one of the permanent components, along with operations centers, data centers, analysis centers, a central bureau, and a governing board. The IGS network is made up of more than 500 permanent and continuously operating stations distributed worldwide. The IVS network has about 40 legacy stations and 15 VGOS radio telescopes. The IDS network is about 60 stations. There are locations where the geodetic techniques are co-located. The collocation is important because it enables the integration of individual technique-specific networks into a unique terrestrial reference frame, the assessment of the observation quality and accuracy. The connection of tropospheric parameters between co-located GNSS station and VLBI radio telescope takes place by means of what we call the tropospheric tie, namely the difference between the atmospheric condition quantified as zenith delay of collocated instruments due to the height difference. In the previous slides, I have shown international ground-based networks, but there are also several regional networks covering, for example, Europe and the Americas. On the left-hand side, you can see the Europe Permanent GNSS Network. As of today, EPN is made up by 424 GNSS tracking stations in Europe. It is operated under the umbrella of the IAG Regional Reference Frame Subcommission for Europe. On the right-hand side, you can see the Circus network, which is made up of about 400 GNSS tracking stations in the Americas and in the Caribbean, operated under the umbrella of the IAG Regional Reference Frame Subcommission for South and Central America. This brings me to the second part of this presentation. I will focus on the tropospheric estimation, how we get zenith total delay and integrated water vapor from the geodetic observation. In this slide, you can see a schematic presentation of individual slant path delay from 3 GNSS satellites and their mapping into zenith total delay. On the ground, there is a GNSS antenna in the middle, a VLBI radio telescope on the left, and a Doris beacon on the right, being the signal of the 3 microwave geodetic techniques delayed by the neutral atmosphere in the same way. In the case of VLBI, we know that the signal is transmitted by a quasar that is not shown in the picture. Such a delay is a noise for geodesy, but is a signal for climate and meteorology. Let us focus on GNSS data processing to figure out how, from the collected data, we estimate tropospheric parameters. The first thing we need are the GNSS observations collected at the ground stations. For analyzing them, we need corrected and updated metadata stored in station site log. We need models, auxiliary informations that are satellite products, this last coming from a global processing. For GNSS data reduction, we need a scientific software at the state of the art with a proper setup for the estimation of tropospheric parameters. When the tropospheric parameters are output of the data processing, a post-processing phase is needed, for example, to detect outliers and to homogenize a long-term ZTD time series in case of climate application. It is important to keep in mind that the delay is not observed, but it is estimated. That means that its accuracy depends on the accuracy of all the other parameters used during the data processing. ZTD can be converted into integrated water vapor, an essential climate variable of the World Meteorological Organization Global Climate Observing System, if auxiliary information, namely pressure and weighted mean temperature of the atmosphere, are available. In the third part of this presentation, I will report on tropospheric monitoring at ground-based network, focusing on EPN and IGS. As of today, EPN is made up of 424 stations. These stations are distributed among the analysis centers in such a way that each station is analyzed by at least 3 of them. This ensures the reliability of the EPN products. In addition to the site coordinates, the analysis center estimates tropospheric parameters, namely ZTDs and horizontal gradients, at 1 hour sampling rate. The individual analysis center solution are the input of the combined EPN products, containing the combined tropospheric estimates with an hourly sampling rate of all the EPN stations. For a single site, ZTD is modeled as the following equation, where Yn is the true ZTD at epoch Tn, Bk is the analysis center bias, and Ekn is the residual between Yn and Ykn. The linear function model can be solved in a generalized least square sense by adding the following constraint equation. The method provides combined ZTD estimates and their standard deviation, site and analysis center specific bias and weight. On a weekly basis, the monitoring is done at analysis center level and at the station level. In the upper part of the plot, you can see the ZTD bias of each contributing solution with respect to the combined solution. The related standard deviation is in the lower part of the plot. This plot shows the performance of each analysis centers with respect to the combination. It helps to identify potential periodic signals and reflect changes, for example, in the used option, analysis procedures, and so on. Such changes are clearly seen in the time series that is made up of two pieces, EPN, repro-true, and operational. The operational time series is made up of two pieces as well. The first is in IGS 14 standards, the second in IGS 20 standards. This time series is not homogeneous, so it is not useful for climate application. It will be replaced by a completely reprocessed time series in IGS 20 standards that will be delivered in the framework of the third EPN reprocessing campaign. Similar monitoring is done at station level. This example is for the Swiss station Zimmerwald, that is one of the two EPN stations analyzed by 7 EPN analysis centers. On the right side of the slide, you can see the plot of the ZTD bias upper part and related standard deviation lower part of each contributing analysis center processing Zimmerwald with respect to the combined solution. What the IGS is doing in the field of tropospheric monitoring. The IGS associate analysis centers generate tropospheric products for all the stations in the IGS network. These products include 5-minute estimates of zenith total delay and north and east tropospheric gradients component. It's a PPP solution and not a combined one that utilizes the IGS final satellite orbit and clock products along with the EOP product. They are available with a latency of 3 weeks following the observation day. The last section of this presentation is devoted to the requirements and application to climate and meteorology. Let's start with climate. The climate requirements are long-term time series. Climatology is based on 30 years. Global coverage, dense regional coverage, and homogeneity. We need homogeneity in the processing option, in the instrumentation, in the auxiliary meteorological data used in the conversion in the ZTD to integrated water vapor conversion. The applications can be divided into 3 areas: numerical weather prediction reanalysis, climate model validation, exploitation of integrated water vapor time series. As far as numerical weather prediction reanalysis is concerned, a reanalysis is made using a fixed numerical weather prediction model with data assimilation for a long period in the past. Reanalyses are used to estimate trends in climate. The better quality observations are, the better the reanalysis is. GNSS-based atmospheric estimates are assimilated in today's reanalysis. Climate model validation. A climate model includes an extended numerical weather prediction model, which can run without data assimilation for a very long period without becoming unrealistic. Running a climate model for a past period, observations including GNSS-based data can be used to assess the skill of the climate model. That way, climate models can be improved. Exploitation of integrated water vapor time series. Water vapor is of enormous importance in the climate system. Instead of using reanalysis data, one can directly study integrated water vapor time series to understand time and spatial variability in the water vapor field, study integrated water vapor extreme, long-term trends, relationship between integrated water vapor and precipitation. Deducing integrated water vapor data about pressure and temperature from the observation or from a numerical weather prediction model. High-resolution European regional reanalysis for Copernicus Climate Change Service is made using numerical weather prediction harmony aroma model that is used operationally at many Met services in Europe, including the Nordic countries. It encompasses conventional observations, satellite radiance, data from aircraft and buoys, scatterometers, atmospheric motion vectors, GNSS radio occultation, and EPN ZTD data. This plot on the left shows in red the control run with no GNSS ZTD, and in green the same run with the GNSS ZTD. For verification of specific humidity, the verification of specific humidity is done against radiosonde. The outcome is that the model is generally too dry and that GNSS ZTD monitors the model at all levels. As far as meteorology is concerned, the requirements are expressed in terms of accuracy, timeliness, spatial coverage, horizontal sampling. For each of them, there are three values: the threshold, the minimum requirement, the optimal, the ideal requirement, and the target, an intermediate between the threshold and the optimal. In the upper part of the slides, the requirements are for hourly ZTD product for global and regional numerical weather prediction, while in the lower part, they are for sub-hourly ZTD product for nowcasting and local numerical weather prediction. The operational use of GNSS data in Europe is done under the EGVAP umbrella, 20 years of collaboration between the geodetic and atmospheric communities. On the left, you can see the European stations, and on the right, the global stations that are contributing to EGVAP. EGVAP is the EUMETNet GNSS water vapor program. The main purpose of EGVAP project is to collect and distribute GNSS-derived ZTDs for usage in operational weather forecasting in near real time within 90 minutes. There are 25 analysis centers, mainly from geodetic institutions and on voluntary basis. The operational assimilation is done at many European national Met services. The use of EGVAP ZTDs has proven positive impacts on numerical weather prediction forecast skill. Using pressure and temperature estimates from meteorology, ZTD can be converted to integrated water vapor to create 2D maps of integrated water vapor for use by forecasters. This slide shows the impact of GNSS data on numerical weather prediction forecast. In the middle, you can see the hourly precipitation as observed by the radar. On the left, you have the precipitation forecast obtained without GPS, while on the right, the precipitation forecast obtained with GPS. The improvement achieved with GPS data is clear. The histogram on the left shows the impact per observation at various types of observation in the UK Met Office global and numerical weather prediction, with GNSS delays having the second largest impact. It demonstrates that both that GNSS delays are useful and that numerical weather prediction system is far from being saturated with this type of humidity data. Additional GNSS ZTD will benefit the numerical weather prediction system. In more than 20 years of GNSS meteorology in Europe, outstanding results have been achieved due to a fruitful cooperation between the atmospheric and geodetic communities. Thanks to that, GNSS tropospheric products are now used for operational weather prediction applications like numerical weather prediction, nowcasting, and monitoring severe weather. There are challenges and developments in the fields to be faced in the next year. Several numerical weather prediction setup requires ZTD with improved timeliness. High-resolution numerical weather prediction will benefit from greater spatial resolution. It turns out that we have to move from hourly to sub-hourly processing. So far, only ZTD is assimilated. The impact of using ZTD gradients or slant is being tested with promising results. Unclear so far whether use of ZTDs adds skill relative to the use of ZTD gradients in NWP. As an alternative to NWP assimilation, GNSS tomography can be used to estimate the 3D refractivity field or the 3D water vapor fields, which can be used in numerical weather prediction assimilation or by forecasters. It requires a very high density of GNSS sites or additional data to constrain properly the tomographic solution. Forecasters will benefit from real-time integrated water vapor data from nowcasting of severe weather events. This requires real-time data, real-time products, and real-time processing. Regarding the impact of using gradients, I'm showing this very promising sensitivity experiment. Two GNSS networks with stations distributed at approximately 0.5 and 1 degree distance from each other were considered, as shown on the left-hand side. The results showed that assimilating ZTD led to an improvement in humidity. Moreover, where gradients are assimilated on top of ZTD, from a sparsely distributed network, more information to correct the analysis data are given. This allows to maximize the humidity field improvement at places where with fewer GNSS stations. Additionally, in the comparison with respect to ERA 5, it is observed that gradients performed at 1 degree network, red line, are roughly the same as the assimilation of ZTD alone at 0.5 degree, blue line. This study shows the sensitivity of tropospheric gradients and zenith wet delay during EV local set precipitation events. The outcome is that GNSS is a useful and expensive tool to study the horizontal water vapor distribution before, during, and after precipitation event. This concludes my presentation. I sincerely thank all of you for your kind attention.
Agradecemos a la doctora Rosa Pachone. Ella no nos avisó que no iba a poder estar, así que si tienen alguna pregunta, se la vamos a hacer llegar por correo. Rosa couldn't assist online, so if you have any question, please write in the place, and I will send to Rosa the question. Well, the other presentation is from Jan Dousa. He's a research from the Geodetic Observatory in PECMI and the Research Institute of Geodesy, Topography and Cartography from Czech Republic. The presentation will be in GNS Real-Time Tropospheric Monitoring. Tendremos ahora la presentación de Jan Dousa. Él es del Instituto de Geodesia, Topografía y Cartografía y del Observatorio Geodésico de PECMI en República Checa. Tenemos su video y está presente para hacerle preguntas luego del video.
Good morning, good afternoon, good evening to everyone. My name is Jan Dousa, and it is my pleasure today to present my third topic, GNSS Real-Time Troposphere Monitoring. Let me start the talk with a brief introduction with background information. I will then focus on real-time processing strategy developments and demonstrations. Finally, I will describe the state-of-the-art operations and validations. The concept of GNSS methodology has been introduced by Rosa Pachone. It is turning a noise in geodetic applications into well-established parameters useful in meteorological applications. GNSS signal is delayed and banded by the atmosphere. Both effects are attributed to atmospheric constituents commonly parameterized in numerical weather model NWM. The interesting one is the water vapor, or its integral value in profile, to which GNSS-based signal delays can be converted. The bottom figure shows the integrated water vapor parameters stemming from two GNSS solutions as well as derived from numeric weather model. Obviously, precise GNSS is able to capture high temporal changes in water vapor distribution and not observed in numeric weather model. The concept transformed GNSS receiver from a positioning tool to an atmospheric sensor. The standard observation model for the troposphere introduces zenith tropospheric delay, ZTD, parameter which consists of hydrostatic and wet contributions. Both are projected into the line of sight by the so-called mapping functions. An extended model adds horizontal linear gradients along with ZTDs. However, for gradients, wet and hydrostatic contributions are combined. High temporal variations or high spatial anisotropy effects could also be observed in carrier phase residuals along with other unmodel errors. Slant path delays could be then retrieved from the post-hit residuals and estimated parameters, hence bringing advanced information for 3D water vapor reconstruction or monitoring extreme weather. Anyway, residuals should be clean of systematic error for such as a multipath effects. All information derived from GNSS analysis are of interest for nowcasting and several weather monitoring applications. For completeness, I would like to mention also hydrometers, the effects due to the presence of liquid water, ice, snow, cloudbursts in the atmosphere. Also, the effect is very small. It is closely related to several weather conditions, thus raising a strong interest for nowcasting applications. Two figures now shows spatial and temporal occurrences of this effect caused by the liquid water during heavy precipitation in Central Europe. The difference between weather forecasting and nowcasting is explained to better understand requirements on GNSS products. Forecasting is based on numerical weather predictions, employing models of physical atmospheric parameters. Its typical range is from hours to days. On the other hand, nowcasting maps the current weather by applying simple visualization and extrapolation methods, underlying only optical flows. Typical range is between 0 and 6 hours. While the requirements on the GNSS ZTD accuracy remains the same, the difference lie in latency and temporal and spatial resolutions. A brief overview about the development of GNSS methodology includes significant international projects. Since 2005, the EGWAP coordinates operational near-time solutions. Gray color indicates mandatory prerequisite for GNSS precise analysis, data flow, precise products, models, and services. Blue color represents the demonstration and operational analysis. Brown boxes introduces operational utilization in numerical model analysis. Red color then represents real-time related production. The box frame finally represents target developments of continuous GNSS tropospheric multiparameters products delivered with an unprecedented time resolution and almost no latency. Traditional real-time batch solution relies on the least square estimator using deterministic parameterization and double difference observations. This strategy still dominates among EGWAP services. Its main advantage lies in eliminating satellite clocks and biases. Real-time PPP was enabled by the IGS real-time service, streaming state space corrections for satellite orbits, onboard clocks and biases. The PPP supports absolute troposphere estimates, however, requires accurate models and their consistency with the correction service provider. The PPP support implicitly the processing in a global scale as well as at remote stations. It is particularly popular for an efficient handling of real-time and multi-GNSS data, for high temporal parameter resolution, for simple retrievals of advanced tropospheric parameters. The PPP driven by real-time inputs and combined forward-backward filters was used for developing also all-in-one strategy adaptable for simultaneous real-time and real-time production. Real-time versus near-real-time processing is trade-off between the accuracy and the latency. Standard least square solution uses deterministic models, like a piecewise linear piecewise constant, which may result in discontinuities of estimated parameters at boundaries of each batch solution. The real-time PPP is then driven by a continuous forward filter for stochastic estimates of tropospheric parameters. The PPP is capable of providing simultaneously near-real-time solution in blue circles if backward smoothing is additionally applied. The main deficiency of real-time filtering is shown on this plot. A fast decrease in ZTD 7 cm per 4 hours demonstrates how is the forward filter capable to reflect such a fast change. A priori sigma for the random walk noise is commonly introduced empirically. In this way, it can easily be underestimated or overestimated. The former causes a slow adaptation of ZTD to last observations. The latter may cause generally decreased accuracy of ZTD by overweighting recent observations over past ZTD estimates. An optimal noise should consider actual troposphere dynamics. A smooth solution indicates a potential 20% improvement in accuracy of estimated ZTD, however, on the cost of increased product latency. The smoothing effect increases with the length of the period. In other words, the accuracy increases thanks to the contributions from recent observations to the older ZTD estimates. The scheme shows inputs-outputs for real-time PPP. Station metadata and models are introduced from files. Also, tropospheric outputs are regularly saved in files in the TropoSynX format. Observation data, navigation data, and precise corrections are continuously streamed over Internet using the N-trip protocol. The N-trip caster enables flexible dissemination of any data streams. Real-time PPP engine collects input data with parallel N-trip clients connected to the N-trip caster. The software needs intensive threading for simultaneous input data and output data handling and station processing. Observation data and global navigation data are collected from individual streams. Orbit and clock corrections are made available from various data sources. For example, combined solutions from the IGS real-time service or individual correction services providers. Recently, a unique source has been provided by Galileo High Accuracy Service via signal in space, that's directly from satellites, but also via internet dissemination. Quality of SSR corrections is critical for real-time PPP solution. A snapshot of evaluation of different correction sources includes 5 years of IGS real-time service and 1 year for Galileo High Accuracy Service. Typical accuracy performance 1 sigma is 5 centimeters in 3D satellite position and 5 to 10 centimeters for onboard clock corrections transformed to the units of length. The availability and robustness is also important, along with the continuity and support of individual satellite constellations. Nowadays, IGS real-time service supports all global GNSS constellations, while Galileo High Accuracy Service only Galileo and GPS systems is a typical performance of 5 to 10 centimeters in 3D satellite positions and 10 to 20 centimeters for corrections. Such a lower accuracy compared to the IGS real-time service is attributed to less global stations used for the product generation. Real-time tropo monitoring was triggered by the IGS real-time service in 2013. Several studies were initially performed within the cost for SWEC action, for example, the impact of corrections extrapolation, visible in top left figure, the impact of simultaneously estimating ZTDs, and receiver position using statics or pseudo-kinematic processing mode, left bottom. Both these processing modes confirmed satisfactory results for supporting an estimation of real-time ZTDs from moving platforms. Besides, 3 software packages and 2 extra strategies were assessed for revealing a readiness for continuous real-time ZTD estimates. In April 2013, initial ZTD instabilities were improved by completing all critical models in the software left side. Routine solutions started by evaluating 2 IGS correction sources, IGS-01, IGS-02, and a CNES individual correction source. Mean ZTD standard deviation achieved a sub-centimeter level quality, however, large systematic errors remained, even though they were steadily reducing. A consistency in models between client and service are critical in PPP analysis. Finally, similar results were achieved for European as well as global stations, confirming an implicit support for a global production. Station statistics were computed with respect to the UREF combined and IGS final reference product. ZTD biases are displayed on the left-hand side, standard deviations on the right-hand side. Precision is characterized by 10 mm, only a bit worse for global stations. High variability among stations is visible for systematic errors, still dominating the initial production, and attributed to the lack of knowledge about model consistencies. A better quality of corrections from CNES compared to IGS suggests an issue with full consistency of inputs within the combination, since theoretically the combination should bring the most reliable and accurate product. The GNSS for SWEC action also organized real-time demonstration campaign for motivating various groups to contribute to development. Altogether, 32 European and global stations were selected, although not everyone could process all stations. Some solutions included the second constellation, GLONASS, or horizontal gradients. Assessment proved that the quality is already satisfactory for nowcasting applications after reducing systematic errors to an acceptable level with respect to the precision. GNSS for SWEC benchmark campaign, designed specifically for severe weather monitoring, was additionally used for simulating real-time tropospheric estimates. The campaign was organized in Central Europe during May-June 2013, when repetitive heavy precipitation caused severe floods in the area. Simulation helped assessing the impact of real-time strategy and the products compared to the post-processing ones. GNAT software was ready for both simulated real-time and post-processing solutions using PPP and Kalman filters and smoother. Two reference solutions were derived using two scientific software, Bernice and EPOS, both applying least square batch adjustment with purely deterministic models. Network versus PPP processing mode remained as a difference. The study confirmed a very good agreement among all the solutions, indicating 10 to 25% of degradations when using real-time corrections instead of precise products. Unfortunately, a common positive bias of 2 mm in ZTD was not satisfactorily explained. Benchmark campaign included several weather fronts with heavy precipitations. 3 plots showed GNSS horizontal gradients estimated by different GNSS software and strategies, including parameterization models and time resolution. We can clearly observe an excellent agreement among all the solutions variants during this very specific event. GNSS gradients reached magnitude up to 7 mm, pointing towards increased water vapor. The integrated water vapor content is visible from two left maps, one using numeric weather model Aladdin CZ and another using GNSS PPP. Excellent agreement is obvious and both solutions involved completely independent datasets. Weather front brought heavy precipitation in northwest to southeast direction. Estimated gradients nicely captured the situation in terms of both magnitudes and directions. It is obvious that GNSS ZTD gradients can play a significant role in nowcasting. It is, however, more difficult to say it about the small gradients below 1 mm, since the uncertainty in their real-time estimates are high, particularly due to the capacity to absorb any unmitigated errors. Last but not least, Benchmark could demonstrate the role of posted carrier phase residuals obtained from PPP. By comparing results at 2 collocated stations during 2 consecutive days with different weather conditions, we can notice a large scatter at both stations on June 20. This proved that the residuals could be suitable at least for indicating extraordinary temporal or spatial water vapor variations. Ionosphere-free linear combination of original observation is traditionally used for eliminating the first-order ionosphere effect. PPP raw observation model was introduced in 2011 for exploiting original observations at the dual, triple, and quadruple frequencies. The model keeps original noise of signals when avoiding its amplification due to the ionosphere-free linear combination. Slant ionosphere path delays plot at ground pierce points in figure represents a useful side product. Disadvantages can be seen in a higher complexity, more parameters to estimate, and needs of code and interfrequency biases. PPP raw model was assessed in parallel real-time operation along with the standard PPP model. 3 years of comparisons demonstrate a very good agreement, if not considering the period prior June 2022. Initial degradation in both solutions were caused by a mistake, not correctly introducing satellite PCO-PCV models. The quality was assessed by monthly mean ZTD RMS over all stations with a reference given by UREF combined product. Additionally, RMS were calculated from ZTD differences at collocated stations. GNSS low-cost receivers with dual frequency carrier phase observations became available on market in 2019. 2 such receivers, GOP-B and GOP-C, were connected to different antennas nearby the geodetic reference station, GOP-E. Real-time ZTDs and gradients were then estimated simultaneously employing PPP ionosphere-free and raw models using the same software and precise corrections. GOP-B shows very good agreement with respect to the reference source station, However, GOPC resulted in values degraded by a factor of 2 or even more. This is attributed to the simple patch antenna at GOPC, revealing its strong impact on the results. Generally, GOP-B instrumentation suggests feasible and affordable solution for densification of GNSS atmospheric sensing in real time. Additionally, snapshot of the TD time series from GOP-B is compared to collocated GOP-E and GOP-6 reference stations. Closely collocated station proved to be an excellent setup for advanced validation of any GNSS tropospheric parameter. 10 dual stations were selected in Europe for assessing operational products. Table summarizes the station list, including instrumentation, horizontal and vertical distances. Statistics on left side are computed station-wise using ZTD differences from real-time solutions compared to reference one. Contrary, statistics on the right-hand side consider ZTD differences between dual stations. A significant reduction over 50% in all statistics demonstrate a strong correlation between collocated stations. This is caused by common errors from real-time products and possibly by real-time modeling. Achievable accuracy seems to be limited primarily by the quality of the real-time corrections and employed ZTD parameterization. Evaluation of different correction sources showed that IGS-01 epoch-wise combination provide the best performance. A similar precision was achieved also with the CNES product, however, with higher positive biases indicating some problem with consistency of processing models. Yearly time series of ZTD and gradient differences were calculated between GOP-E and GOP-6 and showing typical fluctuation in quality and of estimated tropospheric parameters. Variations are slightly higher during summer months, which corresponds to theoretical expectation. Strong similarities can be easily observed. Yearly time series of ZTD and gradients differences now from dual stations show a dramatic reductions of original discrepancies. This is an evidence of presence of strong correlations at dual stations attributed to a common impact of using precise corrections, which is particularly true for estimated gradients, extra sensitive to absorption of any mismodeling errors. The real-time estimation of gradients still remains challenging for nowcasting applications. Several operational real-time solutions are running in different spatial domains, European, global, and regional. Networks are split to clusters and for easy validations include some collocated stations. Over 350 stations are operationally analyzed with ZTDs and horizontal gradients stored for every 5 minutes in sub-hourly output troposynix files. SSR corrections from Galileo High Accuracy Service were compared with those from IGS and CNES. 3 solutions were assessed for HAS: Galileo only, GPS only, and GPS and Galileo combined. In addition, GPS solution from IGS and combined GPS, Galileo, and GLONASS from CNES were included. Monthly statistics were computed using ZTD differences with respect to the UREF reference product, and additionally in between collocated stations. The CNES multi-GNSS solution performed the best, achieving ZTD accuracy of 4 to 6 mm for individual stations. The GPS solution from IGS performed as the second best. The Galileo HAS provides less accurate clock corrections for GPS compared to Galileo, which may explain a worse standalone GPS product, characterized with ZTD accuracy of 9 to 10 mm. The standalone Galileo solution from HAS is more accurate compared to the GPS and Galileo solution. Similar results were achieved by inter-comparisons at dual stations, with RMS improved by a factor of 2 or 3 when compared to individual stations. Galileo high accuracy service is also operationally used now in global real-time ZTD estimates. Table shows the evaluation of ZTDs reaching RMS below 10 millimeters. The exceptions are Kourou stations and stations from the Pacific and East Asia area, marked in gray, which are located outside Galileo high accuracy service supported area. Figures eventually shows sample time series of ZTDs and ZTD differences at the Yellowstone station. At the end, the operational web monitoring portal is introduced. It serves for fast visualization of real-time tropospheric estimates, including interstation and inter-product comparisons. The portal is publicly available, and for practical reasons, it is updated only every 1 hour. It enables interactive browsing of different networks, regional, European, and global, with colors indicating different processing clusters. The second video focuses on time evolution of ZTDs estimated from 4 GNSS permanent stations in Sweden and Finland. ZTDs at all stations follows the pattern of fast decrease in ZTD, but delayed in time. The last video shows the collocated station at Onsala Space Observatory displaying a consistent 2 production lines at Onsala Station when using CNES and Galileo high accuracy service corrections. Then the similar production lines and results are showed for the Onsala 1 stations. Thank you for your attention.
Thank you for your presentation, Jan. I could see that there were some questions in the question and answer, and Jan could answer this. Well, if there are more questions. No more questions? Ask about Kyriakos. You mentioned about a software that you use. Can you please give to us more details about this software?
Hi. Yeah, so can you hear me all right? Hi.
Yes, we can hear you.
Good. Okay. So yeah, so we have developed a software package at the it's been in development at the GFZ. It has been used from us for many years, and we finally release the code. Main author is Florian Zeus. He's a known ray tracing expert. The software that we provide to the public is not the first. There are 1 or 2 other software packages that one can download from the internet. There is one, for example, from TU Vienna, the Radiate software. So we did in the paper that we published, we did some comparisons with this software and our software. And we confirmed that the differences are not big, but the big difference is that our software is much faster. And this is because it uses a different approach to calculate the path. It does not do exactly ray tracing. It solves a boundary value problem with Euler-Lagrange equations. And it also allows for some flexibility, so you can choose the the altitude, the orbital altitude of the satellite. You can include or not include the atmosphere. You can put inside any numerical weather model you like. Maybe you have something from SMWF, ERA 5, for example, or maybe you did your own simulations with the weather research forecast model. So all this can be treated with the software. Everything is written in Fortran. There are some MATLAB routines that can manipulate the output of the software. There is a README file, and yeah, so it's very clear. Maybe I can, yeah, maybe I can share the link. So give me a second. While I find this, I'm happy to answer.
I will put a question and please here put the link, please.
Yeah, okay. All right. Okay, so I open question. Okay, RTK-lib. This sounds like a question for Jan. Okay, all right.
Well, thank you, Kyriakos.
All right.
Well, we have only 10 minutes for a break. Please, at 11:30, we need to continue with the presentation of the last session. Please don't continue connecting, please. A todos los presentes, vamos a tener solo 10 minutos de break porque estamos atrasados. Arrancaremos a las 11:30 como estaba previsto la siguiente presentación de la última sesión de la escuela. Por favor, no se desconecten, queden atentos. En 10 minutos continuamos.
¿Continuamos, Virginia?
Sí, Gustavo, por supuesto. La primera presentación de esta última sesión es una presentación de la doctora María Laura Mateo. Ella pertenece al grupo del Centro de Análisis de Atmósfera Neutra de Sirgas y presentará sobre el ZTD y vapor de agua desde estaciones Sirgas GNSS. The next presentation is from María Laura Mateo about the zenith total delay and integrated water vapor from Sirgas GNS stations.
Buenos días, mi nombre es Laura Mateo, soy miembro del Centro de Análisis CIMA, perteneciente a la red Sirgas, que actualmente se dedica a generar productos para el estudio de la atmósfera, dentro del área de estudio de Sirgas. El propósito de esta charla es contarles qué hacemos, cómo lo hacemos y cuáles son los productos que se generan desde Sirgas en relación a los estudios atmosféricos. Como ya se explicó en presentaciones anteriores, la red Sirgas es una red que cuenta con más de 400 estaciones GNSS distribuidas en todo el continente, que además de densificar el ITRF en América, también se utiliza para algunos estudios geodinámicos, entre los cuales hoy nos compete el estudio de la atmósfera. CIMA se encuentra dentro de esta estructura de la red, recolectando los retardos troposféricos que generan los otros centros de procesamiento para poder combinarlos y generar un único retardo troposférico para cada una de las estaciones en el momento de observación. ¿Qué hacemos y cómo lo hacemos? Cada centro de análisis perteneciente a la red Sirgas genera dentro de sus soluciones los retardos troposféricos para cada estación con periodos de observación de 1 hora. En nuestro centro de análisis tomamos cada uno de estos retardos y lo combinamos con el resto de los retardos generados por los demás centros. De esta manera obtenemos una única solución horaria para cada una de las estaciones pertenecientes a la red. Es decir, que generamos 24 retardos troposféricos por día para cada una de las estaciones Sirgas. Este procesamiento se hace gracias a la ejecución de un programa de desarrollo propio, donde se toman los datos de retardo troposférico generado por cada uno de los centros una vez que estén disponibles y los somete a un análisis de calidad. Aquellos retardos que cumplen con la condición de tener menos de 20 milímetros de error con que fueron estimados, superan este control de calidad y son incluidos en la combinación. En caso de no cumplir con este control de calidad, se descarta el parámetro. Una vez que son combinados, se hace un control individual de la solución, a partir de los residuos generados por el ZTD. Si el ZTD combinado cumple con este control de calidad, pasa a la combinación final y se publica el dato. En caso de no cumplir con este análisis residual, se analizan las causas de por qué existen estos outliers y, en caso de verificar que hay un error, el dato no se utiliza en la combinación. Rutinariamente hacemos todo este procesamiento semana a semana para obtener los retardos actuales de los ZTD de las 24 horas del día, para todos los días del año. Este procesamiento lo hacemos desde el año 2013, que es cuando se inició con la tarea de la combinación de retardos troposféricos. Sin embargo, con el reprocesamiento de la red, se pudieron obtener y ajustar al marco de referencia IGS-14 nuevos retardos troposféricos para periodos que no se contaban anteriormente. Es decir, desde el año 2000 hasta el 2013. Se volvió a hacer una combinación de todo este periodo, incorporando estos datos faltantes y obteniendo nuevos retardos troposféricos. De esta manera se cubrió un periodo bastante largo de datos en los cuales no se contaba con la combinación de retardo troposférico. Es decir, que actualmente no solamente contamos con la actualización de los retardos troposféricos semana a semana, sino que también hemos podido reprocesar una gran cantidad de años incorporando los datos faltantes y ya obteniendo una serie de más de 20 años de retardos troposféricos. Es muy importante que previa a la publicación de datos o resultados que puedan ser utilizados para otro tipo de estudios, estos datos sean comparados y validados con otras técnicas o con otros centros de procesamiento. En este sentido, hemos hecho dos validaciones externas. En la primera de ellas hemos comparado los valores horarios obtenidos por CIMA semanalmente con retardos troposféricos de aquellas estaciones que eran coincidentes en el periodo observado con estaciones del IGS. La segunda de las validaciones se realizó con estaciones de radiosondeo, que nos permiten no solamente validar el dato, sino también la técnica, ya que se trata de otro tipo de técnica para medir las mismas variables. En cuanto a la validación del IGS, hemos obtenido muy buenos acuerdos, llegando a una diferencia media de 0,88 milímetros en el dato de ZTD, mientras que el RMS medio alcanza los 6,8 milímetros para el total de las estaciones analizadas. De las 99 estaciones analizadas o comparadas entre sirgas del IGS para el periodo descripto, desde el 2002 al 2023, vemos que se obtienen muy buenos acuerdos, ya que el 40% de las estaciones está por debajo del milímetro de diferencia entre el ZT ajustado por sirgas y el obtenido por el IGS. Mientras que si analizamos los RMS medios para el periodo analizado, en la totalidad de las estaciones, tienen una media de 6,8 milímetros entre las estaciones sirgas e IGS. Aquí abajo les muestro el histograma de los valores medios para cada una de las 99 estaciones durante todo el periodo analizado. Asimismo, podemos ver los valores medios de RMS para el ZTD comparando las estaciones del IGS con las estaciones sirgas, en aquellos sitios donde coinciden. Una vez obtenidos los retardos troposféricos, es necesario transformarlos a vapor de agua. Para ello se utilizan formas ya desarrolladas en conferencias previas, por lo que no voy a profundizar en el tema, en donde además del ZTD calculado por la combinación sirgas, intervienen también la presión y la temperatura en cada sitio observado. Aquí también se ha desarrollado un programa de cálculo que genera rutinariamente los vapores de agua para cada hora de observación, incorporando los valores de presión y de temperatura provenientes de modelos globales disponibles. En nuestro caso, usamos el modelo ERA5, donde obtenemos la presión y la temperatura para cada sitio y para cada hora de observación y lo sometemos a este cálculo riguroso. Finalmente, como resultado, obtenemos las series temporales para el periodo que uno quiera analizar o para el periodo total de observación, tanto de ZTD como de vapor de agua. Fíjense, aquí les muestro dos casos particulares, la estación de Brasilia, ubicada en Brasil, y la estación de UNSA, ubicada en Salta, Argentina, donde podemos ver las series para los 20 años de observación, tanto de ZTD como de vapor de agua. Ahora bien, como expresé al principio, se hacen dos tipos de validación de datos. Una, comparando los retardos troposféricos combinados de sirgas con los obtenidos por el IGS, donde se utiliza la misma técnica de observación, y la segunda, utilizando otra técnica de observación. De esta manera, no solamente se validan resultados, sino también comparamos diferentes metodologías. En esta segunda comparación vamos a usar datos de radiosondeo, tanto de vapor de agua como de ZTD. El radiosondeo es una técnica que se caracteriza por medir medir las variables atmosféricas a partir de la emisión de un globo, el cual va, a medida que se va elevando, va midiendo los distintos valores de presión, temperatura, humedad, etc., a lo largo de las distintas capas y de las diferentes alturas. Esta técnica es muy costosa y se realiza en pocos sitios del área a estudiar. Sin embargo, es una técnica muy precisa. Actualmente se cuenta con una red que publica los datos de toda América en la página de la Universidad de Wyoming. En ese sitio publica los valores obtenidos para cada día de observación. Cada una de las estaciones genera una grilla de estas características donde se puede observar en cada nivel de altura la variable medida de presión, temperatura, humedad, etc. A su vez, tiene datos complementarios como la posición del sitio que se realizó la observación y las características de la estación. Bien, usando los datos, más precisamente la posición del punto de radiosondeo, podemos establecer una relación entre las estaciones sirgas y las estaciones de radiosondeo que nos permitan hacer una comparación. Ubicamos aquellas estaciones que se encontraran una estación de radiosondeo respecto de una estación sirga que se encontraran a una distancia menor a 30 kilómetros una de la otra. Logramos hacer coincidir 54 estaciones de radiosondeo con estaciones sirgas, es decir, que el análisis se hizo en 54 estaciones. Fíjense en este mapa que si nosotros rellenáramos con estaciones sirgas, todos los puntitos negros son estaciones sirgas, rellenáramos con estaciones sirgas los espacios donde no tenemos estaciones de radiosondeo, podríamos tener un conocimiento más amplio del área a estudiar. Bien, entonces ahora vamos a ver. Recordando que al principio, lo que dijimos al principio, que íbamos a comparar las dos variables, ZTD y vapor de agua, entonces vamos a sacar de cada registro de radiosondeo estos dos valores, ¿sí? Sin embargo, el valor que nos da el radiosondeo, en este caso, es el vapor de agua, y debo calcular el ZTD, ¿sí? Entonces, vamos a hacer el proceso inverso al que hicimos con los datos de sirgas. Es decir, para cada radiosondeo vamos a obtener el vapor de agua, la presión y la temperatura. Vamos a hacer el proceso inverso en cuanto al cálculo y vamos a obtener el ZTD para cada uno de los sitios estudiados. Fíjense, acá estamos haciendo una comparación de las series de ZTD para dos estaciones, que pongo como ejemplo, donde se observa cómo se acompañan una estación respecto de la otra. Es decir, hay una concordancia muy buena tanto de los valores de ZTD obtenidos por las estaciones de sirgas como con las obtenidas por las estaciones de radiosondeo. A su vez, se puede observar cómo se pueden completar esos valores de radiosondeo con la gran cantidad de valores observados que tenemos en sirgas, ¿sí? En radiosondeo recordamos que teníamos un valor por día, dos valores y en el mejor de los casos 4 valores por día, mientras que con la red sirgas o con una estación GNSS yo puedo observar en periodos mucho más cortos. En este caso estamos mostrando valores obtenidos cada una hora. Aquí estoy mostrando otro ejemplo similar donde puedo completar la serie de ZTD obtenida con radiosondeos, completarla con valores obtenidos con GNSS. Bueno, si analizamos ahora la correlación obtenida por las dos variables, o sea, cómo se acompañan el ZT obtenido por la combinación de sirgas con el ZT obtenido por los radiosondeos, vemos que hay una muy buena concordancia, ¿sí? Acá estoy mostrando 4 ejemplos diferentes de la correlación obtenida para estaciones ubicadas a distintas latitudes, ¿sí? Una bastante al norte, en el hemisferio norte, otra en Brasil, en una latitud central, y 2 en Argentina y Chile, en una latitud bastante al sur. Los 4 casos que se ejemplifican acá tienen muy buena concordancia. Si analizamos la correlación para la totalidad de las estaciones estudiadas, vemos que la mayoría de las estaciones, o sea, un 80% de las estaciones, tienen una diferencia menor a 1 centímetro de diferencia entre el ZTD calculado por la combinación de sirgas con el ZTD calculado a partir de las observaciones de radiosondeo. Y solamente el 20% están por encima de ese centímetro, pero nunca superan los 2 centímetros. En cuanto a la correlación del ZTD calculado por sirgas y del ZTD calculado a partir de datos de radiosondeo, vemos que más del 90% de las estaciones tienen una concordancia mayor al 95% de correlación y solamente el 10% están por debajo de ese 95%. Bien, validamos ya el ZTD, ahora nos toca validar el vapor de agua. Como el vapor de agua ya era un dato que sacábamos directamente de cada uno de los datos de radiosondeo, podemos hacer la comparación directamente con el vapor obtenido por sirgas y obtener también muy buena concordancia. Fíjense, aquí estamos mostrando, al igual que recién, con los puntitos rosados, el vapor medido por el radiosondeo y con los puntitos celestes el vapor calculado a partir de las observaciones de las estaciones sirgas. En ambos gráficos estamos viendo una de latitud central y una de latitud sur, bastante austral, y vemos lo bien que se acompañan y lo bien que se acomodan los dos valores comparados. Estoy mostrando aquí 4 ejemplos de diferentes estaciones, ¿sí? Donde vemos no solamente que se acomodan muy bien, que tienen una relación muy acorde el cálculo realizado por sirgas con el medido por los radiosondeo, sino también que nos permite completar aquellos espacios donde no hemos podido obtener datos de radiosondeo por diferentes razones, pero sí está la estación GNSS midiendo en ese momento. Con esta conclusión podemos decir que podemos usar valores de GNSS para calcular vapor de agua en aquellos lugares donde no tenemos la posibilidad de medir con radiosondeos. Aquí les muestro la totalidad de las estaciones analizadas y los valores medios para todas las estaciones estudiadas durante el periodo que venimos analizando, desde el 2002 hasta el 2023, y podemos ver la buena concordancia que hay entre los datos calculados, entre el vapor de agua calculado con las estaciones sirgas versus los datos medidos con las estaciones de radiosondeo, ¿sí? Los valores medios están en 0,51 kilogramos por metro cuadrado, mientras que las desviaciones estándar medias están en 2,2 kilogramos por metro cuadrado. Estos son muy buenos resultados. En cuanto a la correlación, el coeficiente de correlación está en un promedio de 0,96%, con lo cual estamos diciendo que estamos casi igualando resultados calculados con los medidos. Bueno, y para ir terminando, como los datos calculados por sirga ya los hemos validado, ya se pueden publicar y ya están publicados, pueden descargarlos de la página de sirgas para hacer uso totalmente libre y gratuito, y los pueden encontrar en 2 formatos, en el formato anterior del SINEX versión 2.0 y en el nuevo formato que establece el IGS para la publicación de retardos troposféricos. Eso es todo de mi parte, les agradezco por haberme escuchado y por la invitación a participar de estas jornadas y de esta escuela en geodesia.
Bueno, a ver si tenemos alguna pregunta. Ahí hemos pegado en el espacio de preguntas el link que nos pasó Criacos sobre el software DNS. Así que todos pueden tener acceso ahí.
What was that?
I tell to the assistants that your link was paid in the space of questions. Thank you, Kyriakos.
Okay. Super.
Well, there is a question for Laura. There is a question from Hermes about the software RT Calib. If you could, Kyriakos, if you can answer to Helmer.
Yeah. I wrote something about. Okay.
He asked, there was significant difference between RTKlib and other software. What may be the cause?
I think this is maybe in the better suits the field of expertise of Jan or Rosa. I've not used RTKlib, so I'm afraid I cannot answer this question.
Okay, don't worry.
Okay.
I will ask this question to Rosa Paccione and I will send the answer to Hermes. Rosa couldn't stay online connected. Well, if there isn't any question, I will ask Gustavo in order to continue with the next video. In this moment, we finish about the troposphere parameters and we will begin with the ionosphere. En este momento concluimos la parte de troposfera y vamos a iniciar las últimas dos presentaciones que serán sobre ionosfera. En este momento tenemos la presentación de Francisco Azpilicueta. Él es docente investigador de la Universidad Nacional de La Plata de Argentina y presentará sobre modelado ionosférico con GNSS y datos de altimetría satelital. The next presentation will be by Francisco Azpilicueta. He's a teacher and research from Universidad Nacional de La Plata from Argentina. He will talk about ionospheric modeling with GNSS and altimetric satellite data.
Buenos días, soy Francisco Azpilicueta, soy investigador y profesor en la Universidad Nacional de La Plata y en el Consejo Nacional de Investigaciones Científicas y Técnicas de Argentina. Quiero agradecer a Virginia McKern y al comité organizador de la escuela por invitarme a dar esta presentación, que trata sobre el uso de mediciones GPS en el estudio de la ionosfera terrestre. Bien, la imagen muestra los temas que abordaré en mi presentación. Daré información básica del sistema GPS, presentaré las ecuaciones del observable de código y de fase. Después hablaré de las combinaciones que se utilizan para obtener la información ionosférica. El paso siguiente será el de procesamiento de las observaciones de código y de fase para obtener información ionosférica precisa. Después hablaré de la técnica de obtención de las constantes de calibración. Mostraré un ejemplo de modelo del TEC sobre una estación a lo largo de un día y modelo del comportamiento del TEC a escala global, también para un día. Finalmente, daré información de las serie de satélites TOPEX y JSONs, que también son sistemas geodésicos que permiten obtener información ionosférica. La técnica que les voy a presentar está específicamente relacionada al sistema GPS, pero es aplicable a los otros sistemas de navegación satelital. Bien, el sistema GPS consiste en 30 satélites orbitando en 6 planos separados aproximadamente 60 grados entre sí sobre el ecuador y a una inclinación de 55 grados. Dan 2 revoluciones por minuto. Y desde el punto de vista ionosférico nos interesa saber que la altura a la que orbitan es de 20.000 kilómetros, es decir, mucho más alto que el límite superior de la ionosfera. Y el otro punto importante es que los satélites transmiten señales en múltiples frecuencias. Finalmente, es interesante mencionar que los receptores GPS son extremadamente autónomos. La figura representa un esquema simple del funcionamiento del sistema GPS. Por un lado tenemos al satélite orbitando a 20.000 kilómetros. Por el otro lado, en el otro extremo, está el receptor ubicado sobre la superficie de la Tierra, y esta línea roja representa el camino que sigue la señal transmitida por el satélite. En el camino hacia el receptor, la señal atraviesa esta región celeste que se corresponde con la ionosfera. El observable básicamente es distancia satélite-receptor. Siendo más específico y apoyándome en las presentaciones de mis buenos colegas Virginia y Galera Monico, puedo escribir la ecuación del observable de código de la siguiente manera. El observable GPS es igual a un término debido a la distancia geométrica entre el satélite y el receptor. Un término que tiene que ver con los offsets de los relojes del receptor y del satélite respecto del tiempo GPS. Un término debido al retardo troposférico. Un término debido al retardo ionosférico. Este es el término que nos interesa a los ionosferistas. Más, después, un término que tiene que ver con retardos de hardware del receptor y del satélite, que después van a ser parte de la constante de calibración, más un término de ruido local asociado al multipass. Finalmente, el término epsilon, que es el ruido de medición clásico. El receptor GPS mide de forma simultánea código y fase. La ecuación de acá arriba representa a la medición de la portadora de fase, que es igual a un término debido a la distancia geométrica satélite-receptor, término asociado a los offset de los relojes respecto del tiempo GPS, un término debido al retardo troposférico, el término debido a la ionosfera, que es el que nos interesa. Aparece un término propio de la observación de fase, que tiene que ver con una ambigüedad, y después retardos de hardware del satélite y del receptor. Finalmente, un término debido al multipass del sitio y el epsilon asociado al error de medición clásico. Para extraer la información ionosférica recurrimos a la conocida como combinación ionosférica o combinación libre de geometría, que consiste en hacer las diferencias entre pares de mediciones de código de 2 frecuencias, como se muestra en la imagen. Esta observable se lo identifica como P4 y es igual a un término debido al retardo ionosférico sumado a un término asociado a las constantes de calibración. Estas constantes de calibración se las suele llamar differential code biases, asociados uno al satélite y el otro al receptor. Los gráficos de la izquierda muestran un ejemplo de cómo se ven las mediciones de P1 y P2 a lo largo de un día. Esto son mediciones obtenidas en una estación, Padua, en Italia. Cuando hacemos la combinación P4, el resultado aparece en el gráfico de la derecha, donde podemos identificar un patrón asociado a la ionosfera, donde muestra un pico cercano al mediodía local, y también aparece claro el error debido a la constante de calibración. Fíjense que hay un conjunto de valores negativos que no deberían aparecer. Eso es un indicador de que algo todavía hay que hacer sobre la observación. Aplicando la misma combinación libre de geometría a pares de observaciones de la portadora de fase a diferentes frecuencias, obtenemos el que se conoce como observable L4, que es igual a el término ionosférico más un término debido a las ambigüedades y un término debido a los retardos de hardware de fase de las observaciones de la portadora. Los gráficos de la izquierda muestran el comportamiento del observable L1 y L2 a lo largo del mismo día y sobre la misma estación de los gráficos anteriores. Y el gráfico grande de la derecha muestra el comportamiento del observable L4. Fíjense que en este gráfico no es simple identificar el patrón esperable de la ionosfera. Fíjense que toda la dispersión va cambiando a lo largo del día, y esto se debe principalmente al problema del término relacionado a las ambigüedades. A diferencia de las observaciones de código, este término no es constante a lo largo del día. Por eso que el gráfico muestra este comportamiento tan diferente. En este punto podemos resumir las principales características de los dos observables que generamos, el P4 y el L4. El P4 es ruidoso porque tiene que ver con mediciones de código. No tiene ambigüedad y tiene problemas de calibración, ¿no? Los dB que mencioné anteriormente. Por otro lado, tenemos el observable L4, que es mucho más preciso que el observable P4. No tiene problemas de calibración, pero sí tiene un problema asociado a las ambigüedades. La comunidad ha desarrollado varias técnicas que permiten aprovechar las ventajas de cada observable. Una de ellas es la técnica conocida como Carry-to-Code Leveling, que utiliza el observable de código para resolver el término de ambigüedad de la fase. La forma en que se realiza este procedimiento es calculando el promedio de la diferencia entre L4 y P4 a lo largo de un arco. Ese promedio es igual al término de ambigüedad más los dB del satélite y del receptor. Utilizando esta constante para corregir la observación L4, obtenemos la que se conoce como L4 tilde, es decir, nivelada, que es el L4 menos ese promedio. Y el resultado está dado por la expresión de abajo, que es igual entonces a la información ionosférica, que ahora ya le ponemos forma como slantec, más el dB del receptor más el dB del satélite. Esta observación es precisa, no tiene ambigüedad y tiene el problema todavía de la constante de calibración. Algunas figuras para graficar el procedimiento que presenté anteriormente. El gráfico de arriba es el comportamiento de P4, el gráfico de abajo es el comportamiento de L4, son los mismos que vimos anteriormente. Al hacer el procedimiento de leveling, del carry-to-code leveling, y obtener el L4 nivelado, obtenemos lo que aparece en el gráfico de la derecha. Fíjense que tenemos ahora sí volvemos a tener el comportamiento, el patrón esperable de la ionosfera con un máximo cercano al mediodía. Estas observaciones, como son de fase, son mucho más precisas que las de código, pero todavía, como les decía, tenemos el problema de la constante de calibración, que en el gráfico se ve claro por este conjunto de valores negativos. En este punto, me gustaría definir qué tipo de información ionosférica provee GPS. Entonces, para eso uso el gráfico que vimos anteriormente, donde tenemos el satélite GPS